uninhibited growth is interesting, but a lot of the times it is unsustainable in the real world. Like say with, for example, populations of humans or populations of animals or fish or whatever. Often they will go through periods of exponential growth due to the reasoning of, well, again, the more we have, the more they will grow. But the environment has its limits, like food supply or water supply or whatever else, where at some point there are too many fish to be sustainable in a lake, or too many people to be sustainable on the earth. And there has to be some point of balance or a limit to that, often in the form of a horizontal asymptote on the graph. But basically what function models such a thing is at the beginning it undergoes the exponential growth with that exact shape following rapid, the slope is very proportional to the current position with that same exponential shape. But at some point it levels off and kind of reverses the exponential trend, trending towards the horizontal asymptote. And this function is called a logistic function. Deriving it, you can do so. We're not going to talk about why it makes sense in this video, but a general logistic function is shown here, where the limit of the growth, and as x goes, or t in this case goes to infinity, it would approach that particular value is always going to be in the top of a fraction, and it's divided by 1 plus b e to the minus kt. Where there's a specific way to find b depending on your parameters. Again, we're not going to get into the details of this, but let's just look at an example. So it says subscribers to an internet-based sales service are modeled by the following logistic function where n is in millions. So it says that it's 20 divided by 1 plus 300 e to the minus t. And also, I forgot to mention k. You can have a growth rate which is dependent on k, which again will affect the speed at which it grows. So here there is no k, which indicates actually 100% growth rate, or 1, which would be quite rapid. But if you're familiar with how internet sales works, usually due to word of mouth or whatever reason, they tend to explode, get really huge really fast, and then often will level off. Or even if the business model was not very good, will actually reverse. Because again, some logistic functions can model the growth rates of real, businesses. But over time, if it's not sustainable or if there's problems with the business model, it will actually lose a lot of those customers that they got in the initial explosion. But let's just go ahead and look at examples. Let's find the number of subscribers after 1 year, 2 years, and 5 years. So that would just be plugging it in because we have the logistic function. We already know those things. And if you wanted to create one yourself, you could it would be a matter of trying to figure out, well, what's your limiting factor, what's your targeted amount of subscribers, and then how fast is it growing, and b depends on the intercept and other things. Anyways, so n of 1, because it does not specify that t is in years, but t is in years just because usually your growth rate is in years as well. But the number of subscribers after 1 year will be given by 20 divided by 1 plus 300 e to the minus 1, or divided by e if we wanted to change it to a fraction, which doesn't really matter, but I'll go ahead and type that in. 20 divided by, make sure you use parentheses around the bottom of a fraction, depending on which calculator you're using. And I'll just go ahead and type it in as e to the negative 1, which gives me approximately 0.179, or if we round that, about 0.18. And the original function said that it was in millions, so this would be 0.18 million, which would be 180,000 subscribers. So not bad. Again, you could figure out, well, what's the initial subscriber count by plugging in 0, and that's another way you would, like, say you had an actual business and you knew how fast you were growing and you knew your subscriber count, you could use those to figure out b. But you would also need to know, well, what is your assumed limit on your customer base, which sometimes that's hard to know, but you can use other businesses for comparison sometimes. And then what about n of 2 and n of 5, the number of subscribers after 2 years and 5 years? Well, again, we can plug in the same thing, so I would just need to change this to -2 to adjust for 2-year growth, which would leave me with 0.48, or approximately 480,000 subscribers. And then after 5 years, we'd expect it. Also, we expect it to grow. Like here, if I'm imagining this graph as my subscriber graph, the limit of the subscribers is going to be 20 million, which is quite a large number. I mean, actually, for some businesses, that's not very much. Like thinking about things like Amazon or Netflix. Well, actually, I don't know their subscriber numbers off the top of my head, but you can imagine. With the internet, it allows for huge businesses that were never possible beforehand. Anyways, but the starting subscriber value is very, very small, and with a lot of businesses, they do start out. Obviously, you got to start somewhere, and it often takes a long time for businesses to grow very, very, up to a large scale. But again, it all comes down to the rate of growth. But it should be getting rapider and rapider at a particular point in time. At some point, it will then level off. So, again, after 5 years, we can see what our subscriber count is. And it's going to be at approximately 6.6 million subscribers. And we can see it's growing very, very rapidly. Not undergoing linear growth. Again, we could graph the function, etc. if we wanted to, but it'll have this basic shape. And also, let's say we wanted to look at, well, what about 20 years down the road or 50 years or something? Again, the point of a logistic function is that it will level off towards that value which appears in the numerator. So, if we plug in, say, 20 years or 50 years, we won't see any difference because it's leveling off and we get approximately 20. So another question we could ask is find the rate of growth, for example, calculating tangent lines using calculus to analyze this further. But basically, this will take the exponential growth. It'll have a growth rate proportional to the initial size for a while. And when it reaches a certain point, which is sometimes called an inflection point, it will switch to the other direction and it will start losing. Technically, you're always gaining subscribers in this model. Notice it's always increasing. However, at a certain point, it's our rate of growth is getting bigger, and then at some point, our rate of growth starts getting smaller, even though we're still growing regardless. But we could use the derivative to help analyze such things. So let's start with the rate of growth. That would just be the derivative n prime of t, or ddt of the original function. So I need to take the derivative of this. Since it is it involves division, I could use the quotient rule to do this. There are other ways, but let's just use low d high. So low. Actually, notice d high would be 0 because the top is a constant. So low d high would be 0 minus high d low. And the derivative of the bottom, derivative of 1, is 0. And the derivative of 300 e to the minus t, the 300 coefficients do not affect the derivative, so we'd have 300. And then derivative of e to the negative t, well, derivative of e is always exactly itself, so that would be e to the minus t. And then the chain rule says I have to take the derivative of the inside anytime there is anything beyond just x or t or whatever your variable is. So since it's just, since it's negative t, I got to multiply by the derivative of negative t, which is negative 1. And that would leave me with my numerator. So again, low d high was 0 minus high d low. And then we need to square the bottom. Away we go. That would leave me with... And that will be equal to 6,000. Because negative times negative equals positive. 20 times 300 is 6,000. E to the negative t divided by 1 plus 300. E to the negative t quantity squared. And if we wanted to know how rapidly our graph is changing after 5 years, we could plug in n prime, plug 5 into n prime. And that would give us, of course, 6,000 e to the negative t. And actually, if you wondered why I transitioned from videos, I accidentally made a mistake and forgot a 0 and had to re-record this, but no matter. Mistakes happen to all of us. And this would leave us with 1 plus 300 e to the negative t. One of the better things about teaching in person is you guys catch my mistakes and it prevents me from wasting time. But no matter, what we end up with is, sorry, I'm clicking the wrong buttons, approximately 13.38. Okay. Let me just make sure I typed all that incorrectly. Did I remember to square it? I did not. So let me make sure that I square that. And that would be approximately 4.42. Yeah, I thought that answer looked wrong. But yeah, we got about 4.42. Let's just round it. 4.43. Round it to the nearest hundredth. But since again this is in millions, this would be, well, really about 4.5 million subscribers. And also remember that your derivative, the units of your derivative have the same units as your original function, except they're always a rate of change. So it's always in millions per the unit of x, or t in this case, time. So this would be basically about 4.5 million subscribers per year, and that's telling us that we're growing very, very rapidly at this point in time. So we'd expect by year 6 it to be, again, not exactly, because over time it's getting faster and faster, but even more than 4 million, maybe something like 11 million, or in that ballpark, due to our growth rate. And as I said before, this is how you could figure out the logistic function to begin with, is figure out, well, how rapidly are we growing right now? Use that as a basis, assuming that you are fitting into an exponential growth, to predict what's going to happen. And we could graph this in a calculator by well, the main thing we need to know is, well, what window do we want to look at? But again, usually with these sorts of functions, we want to start at 0, and well, it says graph it over the first 10 years. So I want to know what's the shape after 10 years. But in a logistic function, we always know it's going to cap out at the limit, the inhibiting factor, which was 20, the value in the numerator. And also where it's going to start is the initial population at time 0, which we knew. Actually, we didn't figure out what that was, but it would be, in the ballpark of 100,000 subs, which is very small compared to 20 million. And, it's going to have that logistical curve to it. We do know one data point that after 5 years, well, actually we know 3 data points, but after 5 years it was roughly 6 million, so it was about a little more, about a third of the way up at that point in time, but we should have a shape sort of like that. And I've already typed this in. But basically the window we want to graph is, we can always customize a window by going into window option in our calculator and telling it where we want to graph. But we want our x-min, our domain, to be 0 to 10 and our range to be 0 to 20, which, I already have it typed in. And if we hit graph, actually, sorry, let me delete, I accidentally graphed the wrong thing, but, we have something that looks kind of like that. And we get our logistic shape, which, as we can see, our subscribers grow very, very quickly and they level out. Makes sense, fits the idea. But also, let's say we wanted to find an equation of a tangent line and draw it. Like at this point in time, we know that the slope was about 4.4 million per year, and it's not exactly the steepest point, but it looks like it might be, fairly close to what's called an inflection point. Yeah, we could find the equation of the tangent line. Well, we already know everything we need to, because remember, for an equation of the tangent line, it's always y is equal to f prime of a times x minus a plus f of a. And we already know all those things. In this case, it would be n. I'll just go ahead and write that out in the case of n prime of a, x minus a plus n of a. Because it's always the slope. This is from the slope-intercept or point-slope form equation. It's the slope times x minus x1 minus or plus y1. Y minus y1 is equal to m x minus x1. But this will give us the equation of a straight line with the proper slope and point for the function at that particular location. And since I want to do this when t is equal to 5, that would be our a. So I'm basically going to plug in 5 there for everything. Well, I know n prime of 5 was 4.43. X minus 5 plus n of, and I know n of 5 was about 6.6 million. So simplifying that out, that would give me y is equal to 4.43x. Negative 5 times 4.43. Now I need to finish off the equation. Negative 4.43 times 5 plus 6.6 gives me about negative 15.55. And last but not least, we can actually graph the tangent line next to our curve, go back into y equals to type in this new formula, y equals 4.43x minus 15.55 graph. And then that way we can check to see if that tangent line was looking pretty good. But it seems to check out. Looks like it is the proper tangent line for the curve at that point in time. And there we have it.